Incidentally, astronomical occasions of great scale happen billions of kilometers away from Earth, resounding all through the universe. Presently, a comparable occasion is approaching, causing shock even among researchers. A red giant star, arranged at the outer spans of our system, is communicating unpropitious signs across the universe, caught by the James Webb Space Telescope. Cosmologists have uncovered profoundly disrupting disclosures about this epic heavenly body. As recognized astrophysicist Brian Cox gives a grave admonition, a pressing question emerges. Are we wavering on the edge of seeing a disastrous cosmic explosion that could forever adjust the natural night sky? Prior to digging into additional subtleties, make sure to subscribe to our channel if you haven't already. Now, the burning question waits. Will this blast influence Earth, and will it be noticeable from our planet? Stay tuned as we investigate the answers to these compelling inquiries in this video. In the tremendous span of the universe, where the show of heavenly birth, life, and death unfolds in entrancing wonder, one specific star has recently directed the attention and concern of both cosmologists and the general public. This star, known as Betelgeuse, stands out noticeably as a red supergiant in the constellation Orion, flaunting colossal size and age. While its striking ruddy shade and fluctuating brilliance have long intrigued onlookers, recent events have further heightened interest in this heavenly behemoth. As we dig into the essence of Betelgeuse, we find ourselves nearing the very edge of a potentially stupendous event in the star's life cycle. But what do these changes in Betelgeuse's behavior mean? Might we witness the start of a remarkable grandiose display of impossible extent? Betelgeuse, flaunting a size roughly 1,000 times greater than our Sun, remains a gigantic giant among stars. Its sheer size stretches the limits of human imagination. Picture a star so huge that if it were to take the Sun's place, its surface would expand past Mars' orbit, wrapping Mercury, Venus, Earth, and Mars inside its heavenly grasp. This phenomenal size not only highlights Betelgeuse's physical monstrosity, but also signals its place in the heavenly life cycle. As a red supergiant, Betelgeuse is in the sundown period of its existence, marked by expansion and cooling after a lifetime of fusing hydrogen into helium at its core. Questions arise about Betelgeuse's age. Despite being relatively young in human terms, estimated at around 8.8 to 8.5 million years old, it remains quite old within the context of stellar life expectancies. Its current status as a red supergiant reflects the culmination of millions of years of stellar evolution, characterized by significant changes from a hot blue star to the great red giant we observe today. The journey of stars like Betelgeuse unfolds as a story of constant transformation, driven by the relentless forces of nuclear fusion and gravity. One prominent feature of Betelgeuse's current phase is its striking red hue. This dark red color arises from its relatively cooler surface temperature, in contrast to stars like our Sun. While our Sun shines at around 5,500 Kelvin, Betelgeuse's surface is cooler, starting at around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light in shades of red. However, this color is not just an aesthetic characteristic. It provides insights into the star's physical state, as well as the ongoing processes within its vast gaseous domain. Adding to the interest surrounding Betelgeuse is its unusual color history. Ancient works from Roman and Chinese sources suggest that, nearly 1,000 years ago, Betelgeuse appeared yellow. It was only after the 9th century that Arabic researchers described it as red. This historical shift in color is not only a footnote in astronomical records, but serves as a signpost in the star's transformative journey. The fluctuating brightness of Betelgeuse adds another layer of intrigue. It acts as a semi-regular variable star, meaning its luminosity undergoes periodic variations. This dance of brightness has captivated astronomers and stargazers for centuries. Typically, Betelgeuse follows a 420-day cycle alongside a longer 5-year cycle, noted as far back as 1836 by Sir John Herschel, and perhaps even earlier in native oral traditions. But what truly sets Betelgeuse apart isn't just its shifting brightness but its irregularity. Unlike many stars that follow predictable patterns, Betelgeuse sometimes deviates from its usual dimming and brightening rhythm. This irregularity points to complex and less understood processes unfolding within its massive structure. Recent significant discoveries have captivated astronomers and stargazers globally. When Betelgeuse experienced a surprising and dramatic change, now widely called the Great Dimming, everything started in late 2019. At that time, Betelgeuse, the red supergiant shining brightly in the night sky and a notable part of the Orion constellation, began to undergo a mysterious dimming. The dimming was so striking that it lost luminosity at an average rate of 0.01 magnitudes per day, reaching its lowest brightness by February 2020. Betelgeuse, commonly visible to the naked eye even amidst light pollution, essentially faded. Even amateur observers couldn't miss it. However, there's a critical challenge in tracking the activities of Betelgeuse, the time conundrum. When we observe a star like Betelgeuse, we're not seeing its current state but rather its past, due to the time it takes for light to travel to us. Betelgeuse, located about 725 light-years away, means that the light we see today left the star nearly 7 centuries ago. This time delay complicates efforts to predict and track sudden changes in a star's behavior, as we are essentially witnessing events that happened in the distant past. The dimming of Betelgeuse serves as a stark reminder of the inherent complexities in cosmic observations and the limitations of our understanding when grappling with the immense scales of the universe and the time mystery they involve. The captivating journey of Betelgeuse's astronomical performance was meticulously tracked by Andrea Dupree, the assistant director of the Center for Astrophysics at Harvard and Smithsonian. Along with her team, using the Hubble Space Telescope, they embarked on a 3-year study to monitor changes in Betelgeuse's outer environment. These observations provided an unprecedented understanding of how a variable star like Betelgeuse behaves, with its regular expansions and contractions leading to fluctuations in brightness. The striking sensitivity of Hubble to ultraviolet light enabled the researchers to probe the layers above Betelgeuse's surface, which were partially heated by the star's turbulent convection cells. Furthermore, a detailed analysis of the Hubble spectra, obtained at various intervals throughout 2019 and 2020, facilitated the measurement of material movement within Betelgeuse's outer environment. Specifically, the study focused on the magnesium-2 lines in the spectra, which offer insights into the star's atmospheric conditions. These observations revealed material traveling at speeds of around 200,000 miles per hour from Betelgeuse's surface into its outer environment. This heated and dense material eventually expanded millions of miles from Betelgeuse, forming the precursor to the dust cloud responsible for the star's dimming. Dupree and her team estimated that, during the 3-month event, roughly twice the usual amount of material from Betelgeuse's southern hemisphere was shed. This significant mass loss is particularly notable because, like all stars, Betelgeuse continuously sheds mass, but at a much higher rate than our Sun. The magnitude of this mass ejection and the resulting dimming sparked discussions among astronomers as to whether this event could signal an impending supernova explosion. The proximity of Betelgeuse, located roughly 725 light-years from Earth, adds to the interest. If such an explosion were to occur, it would be visible from Earth, presenting an intriguing opportunity to closely observe a supernova. But the question persists: what does this dimming event mean for Betelgeuse's future? Does it signal an upcoming supernova? Or is it merely a transient phase in the star's vast and complex journey? Various hypotheses have been proposed to shed light on this phenomenon. One theory suggests a stage in the supernova process gaining momentum due to the widespread belief that Betelgeuse is nearing the end of its life cycle. Another widely accepted hypothesis implicates dust, possibly originating from the star itself, blocking our view of Betelgeuse. A third explanation examined changes in the star's photosphere, its apparent surface layer, which could affect its apparent brightness. Comprehensive analysis using diverse observational techniques contributed to unraveling this mystery. Spectroscopic assessments showed a decrease in Betelgeuse's effective temperature, indicating the likelihood of a significant dark spot on the star's surface. This theory found support in observations revealing a temperature drop of at least 170 Kelvin during the dimming period, highlighting significant surface changes. Ultimately, the key to understanding this extraordinary phenomenon came from humanity's careful gaze into space. The Hubble Space Telescope. Hubble's precise observations revealed that Betelgeuse's dimming was likely caused by a significant ejection of heated material into space. This material coalesced to form a dust cloud, blocking part of the star's surface and reducing the amount of light reaching us from Betelgeuse. The formation of the dust cloud was attributed to superheated plasma, which erupted from a large convection cell on the star's surface and traveled through its scorching atmosphere to the cooler outer layers. After cooling, this plasma formed dust particles, resulting in a cloud that blocked light from roughly a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, played a crucial role in reconstructing the timeline leading up to Betelgeuse's dimming. These observations detected signs of thick, heated material passing through the star's atmosphere in the months preceding the dimming event. By December 2019, other ground-based telescopes also noticed the star's diminishing brightness, particularly in its southern hemisphere. Initially, this material appeared brighter than the star's usual luminosity, eventually culminating in the formation of a shadow as it scattered outward and cooled. The suggestion was simple. This outward flow of material and the resulting shadow were responsible for the sudden dimming of the star. The scale of this ejection is truly astonishing, pushing Betelgeuse into the cosmic spotlight. The star expelled an estimated 400 billion times the mass typically released in a standard coronal mass ejection. This expelled material was thought to be enough to offset our moon several times over, marking a major event not only for Betelgeuse but also for advancing our understanding of stellar mechanics. But what are the implications of such a massive release of material for Betelgeuse and the broader theories of supernovae? The traditional wisdom suggests that red supergiants like Betelgeuse routinely shed mass before reaching the cataclysmic peak of their existence. However, the scale of this release challenges this notion, hinting at a potentially more volatile and unpredictable final stage for these stars. Could Betelgeuse be gearing up for its grand finale, a supernova explosion, within the coming centuries? Later research speculated on the timing of such an event, suggesting it may occur sooner than previously expected, perhaps in just a few years. Additionally, the concept of the bow shock adds another crucial layer to the Betelgeuse puzzle. As this enormous star races through space at around 67,000 miles per hour relative to its surrounding interstellar medium, it creates a bow shock similar to the wake formed by a moving boat's bow. This phenomenon arises from the star's outer layers interacting with interstellar gases and dust, offering a spectacular display of the star's dynamic behavior and its interaction with the cosmic milieu. But what about Betelgeuse's recent behavior? Its surface cooling and diminished density, observed following the ejection event, leave the star in a disturbed state, even years later. Hydrodynamic simulations suggest a link between the star's convective activities, the mass ejection, and the subsequent changes in its oscillation modes. This ongoing instability raises questions about the internal processes driving these changes and their potential consequences for the star's future. Additionally, the observed mass loss rate of Betelgeuse exceeds that of many other stars, reflecting a complex interplay of internal forces. Nevertheless, with energy continuously dissipating through shock heating and mass ejection, Betelgeuse's rhythm is shifting. The very nature of these mass losses points to the star's dynamic and somewhat erratic life cycle, prompting astronomers to reconsider their models of stellar evolution.